Okay, I want to talk about completing the square. Okay, so let's just start with the fact that if we square the binomial x plus a, that means, of course, multiply x plus a times x plus a. Means that we write this out as according to the distributive law. X plus a times x plus a is x times x plus a here plus a times x plus a. And then we apply the distributive law again. X times x plus a gives us x squared plus ax. And a times x plus a gives us ax plus a squared. You notice we get an ax both times, so we've got a 2ax. And we get x squared plus 2ax plus a squared. Used to be when people memorized things that everybody knew this. Just a standard formula everybody used. And you might well have memorized it. You might well have had an algebra course that asked you to use this often enough that you internalized it. And you might have forgotten it since then, but it should be familiar to you. If not, well, you know how to do it. Don't have any trouble doing this. Okay, so I want to ask a question now. I'm going to observe that x plus a squared is what we call a perfect square. It's actually the perfect square of a binomial. That is, and this is. Now, when I say a perfect square in this context, I mean a perfect square of a binomial. So, the question now is, what do we need to add to x squared plus 2ax to get a perfect square of a binomial? Well, if you look at this, you see we've got to add a squared. Okay? It's an obvious answer, but most people won't answer the question because it seems too obvious. Okay, so here we have an obvious answer. At least it's obvious after somebody tells you, yeah, that's just what you might think. Okay, the obvious answer is add a square. Because that gives you x squared plus 2ax, which you already have, plus a squared, which is x plus a squared. And that's the square of a binomial. Now this idea of perfect square, of completing the square, because what we've done now is we've completed the square. We had this partial expression here. To complete the square on this expression, we have to add a square. Okay? Turns out that this is a pretty important process, completing the square. Now, if you get into calculus, and this being a pre-calculus course, we assume that you will, you're going to have to use this technique to do certain integrals. Now, you don't necessarily know what that means, but you're going to need it. Also, this is a process that we use to derive the quadratic formula. Okay, and we're going to actually see that, but not today. Okay, well, let's apply this. So the question is now, what do we need to add to each to get a perfect square? Let's say x squared plus 6x, x squared minus 8x, x squared plus 3x, x squared minus 7x. Okay, well, in each case, what we have here would be this part of the perfect square. Any perfect square can be expressed this way. If we just discover what A is, we can see what has to be added. Well, A occurs in front of x, but it's actually 2A that occurs in front of x. So here, okay, let's see. Your 2AX would be 6x, so A equals 3. We add A squared, which is 9, to get x squared plus 6x plus 9. And that is the square of x plus A, okay? And there we have it. And then you want to check. Check by squaring x plus 3 and see if you don't get x squared plus 6x for the first two terms and 9 for the third term. So I'm not going to do that. I'm just going to say check by expanding. This, see that you get this, and see that first two terms are these. Okay, well, that's what works, that's how it works, that's why it works, and what it comes down to is whatever number you got in front of x, well, that's your 2x, so divide it by 2 and square it. So here, now just kind of shortcutting it, well, I'm going to write it out. I just want to reinforce it. Two AX equals negative 8x, A equals negative 4. Add negative 4 squared, 16. And we get x squared minus 8x plus 16. And that is equal to x minus 4 quantity squared. And of course, we check this. And I'm going to want you in the homework to check everything. Okay? Now I said here check by expanding. I just say check this. You're going to do it by expanding this, seeing that you get this, and seeing that this is the same as this. Okay, so this actually gets kind of monotonous. Okay, well, I'm not going to write it all out this time. I'm just going to say, well, if this is 2AX, then 3 is 2A, so A has to be 3 halves. So add 3 halves squared equals 9/4. And you get what? X squared plus 3x plus 9/4. And that equals x plus 3 halves quantity squared. You don't have to write it down, you're going to check this. X squared minus 7x, well, we get A equals negative 7 halves. Add negative 7 halves squared equals 49/4. And we get x squared minus 7x plus 49/4, and that's equal to x minus 7/2 squared. And we check it. Okay? Now, the completing a square can get a little more complicated than this, but not much. If you understand this much, well, that's good for today. Okay, then follow up with the rest of it. Notice that this only works if the coefficient of x squared is 1. So the only complication is what happens when the coefficient of x squared isn't 1. Well, the answer is you factor out that coefficient and then you complete the square on the rest. We'll see that. But if you understand this much, and try to understand not what you do, but you certainly need to understand what you do, but keep thinking about why you're doing this. You're doing this because whenever you square a binomial of this form, you're going to get 2 times ax as your x term. And you're going to want a squared on the end to make it a perfect square. So a is going to have to be half of whatever's in front of x. Okay, so you're going to have some problems to do with this. And it's actually pretty simple and straightforward, but again, I want to see the check on every problem.